Hello everyone, welcome to Exploring Technologies. In this video, I'm going to explain about the comparison of threshold estimation methods which are used for wavelet based denoising. So here I will explore the effectiveness of various noise estimation methods and threshold selection methods used for DWT based denoising. For this purpose, I will apply these methods on the noisy audio of some Indian musical instruments. So let's start this video lecture. Let me show you the contents which I am going to cover. First, I will introduce denoising using wavelets. Then I will explain various noise estimation and threshold selection methods. Then I will implement those methods in the Matlab and will explain the Matlab code. Then we will run this Matlab code and I will apply on the noisy audio signals of some Indian musical instruments. And then in the last, we will discuss those outcomes. We will do the comparison and we will go for result analysis. So let's go ahead. But before going ahead, I recommend you to watch following these three videos. The first one is about the wavelet based denoising of audio signals using Matlab and Simulink. This is the basic video. Here I have explained that how the Matlab and Simulink can be used to denoise audio signals. So this video you can go through to understand the current video. And the second one is about the theoretical aspects of the wavelet, its theory and its applications. And the third one is same denoising implementation for audio signals but in Python. So those who are interested in Python, they can watch this video. So links are given in the description. So now let me explain what is the noise model. So when a signal is transmitted over a distance, obviously it is contaminated by the noise. So the term noise here refers to a random signal which causes the undesired changes in the original signal. The simplest acquisition model is that this is your original signal and this is the noise signal, and noise is added to your audio signal, and that gives you the contaminated signal F-K. So there are different kinds of noises like white noise and non-white noises. So here our basic assumptions about the noise signal Nk is that noise is additive. Here I'm taking the Gaussian noise, white noise actually, with a 0 mean value, and the noise has a high frequency. So denoising means removing this noise signal from the noisy audio signal F-K with help of wavelet transform technique. So this is the wavelet transform based technique. So here I have this noisy audio F-K. It is first decomposed into the wavelet coefficients with help of the discrete wavelet transform, and then the detail coefficients are thresholded with some thresholding rule. And after the thresholding, all the wavelet coefficients are collected, and then with help of the inverse transform, I get a denoised output. There are various methods which are used to estimate the noise variance, and they are used to set the threshold value lambda to threshold all these detailed wavelet coefficients. So this is simple scheme. And now come to the various noise estimation and threshold selection methods. This is a table which shows these methods. The first one is the minimax, then universal threshold, which is also known as a square root log. The rigorous Steen unbiased risk estimated, that is Sure method, heuristic Sure, and then Bayes, empirical Bayes, block, James Steen block method, and false discovery rate FDR. These are the supported Matlab functions. WDEN supports these methods, but WDEN is an old function which is not recommended by the latest version of the Matlab. So WDenoise is the latest function which I will use in this current video also. And now come to the thresholding rules, how the wavelet coefficients are thresholded. So these are two basic thresholding rules. In the first one, you get this 45-degree line. It means output equal to input, so no thresholding. And this is the hard thresholding. So all the wavelet coefficients which lie below the threshold T, they are simply zeroed out, and rest are remained same. They are not changed. In soft thresholding, all the wavelet coefficients which lie below the threshold, they are zeroed out, but other coefficients, they are also scaled down, they are also shrinked. So all the positive coefficients are subtracted by the threshold, and all the negative coefficients are added with the threshold. That means simply subtraction of the threshold value from each wavelet coefficient. So they are also shrinked. So that is soft thresholding. Other thresholding rules are also available, like James-Steen, median, and mean. And now come to these methods one by one. So first I will take very popular one and very simple one, that is universal threshold. So this threshold was proposed by the Donohoe and Silverman, and it is given by the this formula. So threshold value lambda is sigma square root 2 log n. So this n is the length of the wavelet coefficient vector at some scale. Sigma is the noise variance, which is also known as the MAD, mean absolute deviation at the J scale, and it is given by this formula. So that is median of all the wavelet coefficients at J scale divided by 0.6745. So this is a simple calculation. And the minimax criterion, it uses actually a fixed threshold to yield the minimax performance for mean square error against an ideal procedure. Since the denoise signal can be assimilated to the estimator of the unknown regression function, the minimax estimator is the option that realizes the minimum over a given set of functions of MSEs, and it is given by these equations. So your threshold value is sigma 0.3936 plus 0.1829 log 2n when n is greater than 32, otherwise it is 0. So where sigma is again same, that is MAD, mean absolute deviation, as found in the previous universal threshold method, and n is the length of your vector, wavelet coefficient vector, right? And next is the shear, that is Steen's unbiased risk estimate. It says soft threshold evaluator of unbiased risk. So let's suppose you have a vector W which consists the square of the wavelet coefficients from small to large. So for these coefficients, we make a risk vector R, which has values R1, R2, R3, R4 like that, and each R value is computed by this formula. So when we have all these R1, R2, R3 and Rn, then we find the minimum value of the R, and for corresponding index number we get the omega b. I mean, let's say bth is the minimum, so we select the omega b from this vector, and with this formula we get the threshold value lambda. So that is sigma square root omega b, where omega b is the bth squared wavelet coefficients which is at the minimum risk, chosen from this W vector. And sigma is the standard deviation of the noisy signal, which we have already found in the previous two methods. And next is the heuristic shear. This is not a new method. Actually, it is the selection between the universal threshold and the shear method. So it does the selection on the basis of the minimum energy criterion. So let's say I have the lambda 1 which is computed by the universal threshold, I mean square root log, and I have the lambda 2 which is computed by the shear, I mean the previous method, Steen and Bias estimate. Then which one need to be selected, either lambda 1 or a minimum of lambda 1 and lambda 2? That depends on these criterion. When A is less than B, you select lambda 1. When A is greater than or equal to B, you select minimum of these two. So where A is S minus n upon n and B is log 2n power 3 by 2 square root n, that is actually representing the minimum energy. So here S is the sum of the square of the wavelet coefficient. So that is of course the energy of the wavelet coefficients, and n is the length of the wavelet coefficient vector. And there are other methods which were later added into the Matlab. They are new. The first one is the Bayes method. This method uses a threshold rule based on assuming measurements have independent prior distributions given by a mixture model. So because measurements are used to estimate the weight in the mixture model, the method tends to work better with more example. So by default, the posterior median rule is used to measure the risk. Now next is the James-Steen-Block method. This method is based on determining an optimal block size and threshold. Actually, to estimate the variance and to estimate the lambda, we consider all the wavelet coefficients simultaneously. But in this method, they divide the whole wavelet coefficients into the blocks, small blocks, and then on the basis of that we select the lambda. So here it works on the finding the optimal block size and then corresponding threshold selection. And the next is the based on a statistical method, that is a false discovery rate. So this method uses a threshold rule which is based on the controlling the expected ratio of false positive detections to all positive detections. So this method is actually suitable with the sparse data. So these three methods are actually complex. They have their full length research papers. If somebody is interested with these methods, they can go through these research papers. So Bayes method you can find in this Johnson and Silverman paper, that is a needles and straw in the haystacks, and James-Steen-Block on block thresholding in wavelet regression. And for FDR, you can find the Denoising paper, that is adapting to unknown sparsity by controlling the false recovery rate. So these papers you can find on the internet. And now let's see in which method which thresholding rule is applicable. So if you are going for block JS, James-Steen-Block, then the James-Steen method is only supported. No hard thresholding, soft thresholding, etc. is needed. And when you are going for sure, min-max and universal threshold, then you can select either soft or hard. And in Matlab, when you go for Matlab, the default is the soft. For Bayes, the options available are median, mean, soft, and hard. And I mean any of the four you can use, but the default is a median thresholding. And for FDR, only the hard thresholding is supported. So no need to define other threshold rules for FDR in the Matlab. So now let's go for label independent and label dependent thresholding, in which case you have to go for label independent and label dependent thresholding. And what does it mean? Actually, if your signal is corrupted with a white noise, then most of the wavelet coefficients at finest scale, I mean at label will detail coefficients, contribute the noise, and only very few of them contribute to the signal. So in such case, the noise variance and fixed value of threshold is computed from the detailed coefficients at the finest level, I mean from the CD1 only, and this threshold is applied on all detailed coefficients at each level of decomposition. So that is one scheme when your signal is corrupted with a white noise. But if your signal is not affected with a white noise, such as some colored noise, in such case you have to estimate variance at each level. That is proposed by the Johnson and Silverman in 1987. So the thresholding is done on each level with the estimated variance and corresponding threshold value. So that is the difference. So now come to the Matlab implementation. So I have written one main file, Matlab program, whose name is myden.m. Here I have taken the audio of some Indian musical instruments such as pakhawach, tabla, shehnai, flute and tanpura. So I will apply the denoising on these noisy audio. These audio files are in the WAV format and sample at 44.1 kilohertz. So our objective is to find the best combination of the level of the decomposition, wavelet function and the thresholding method to achieve the effective denoising performance. Okay, so this is the output of my Matlab program. So this is the audio of the flute 10-second audio, which is denoised with the sure method and the coil flat 5 wavelet and decompose at level 4. So this is my original noise free audio, and this is the audio which is contaminated by the noise. You can see the difference. See this thickness. and this is the denoised output. So you just compare the first one and this denoised output. You can find something is happening in the action, but in this figure you can see the denoising more clearly. So this is one segment of that flute audio. Few samples have taken. So this is a noise free, and this is a noisy audio, and this is the denoised output. So you can see that how the denoising is working. Later when I will run the program, I will make you listen the audio, then you can have the idea that how denoising is actually taking place. So this is my Matlab program, myden.m. Here with the UI get file, I am just selecting my audio input, and then I'm checking whether the audio is a stereo, I'm in the 2-channel audio or single channel audio. So if it is 2-channel, then I'm converting it to the single channel. Then defining the DWT extension mode, periodization, and then adding some noise in that audio X. So I'm adding the white Gaussian noise, and then this is for denoising. So W denoise function is used here. So this is your noisy audio. Denoising method is a sure, and these are all other methods. So you can just replace sure with all these methods to get the denoise output. And this is the label of the decomposition, and then wavelet type is a QoI5. So here again you can change the name of the wavelet, and here SNR is computed, and then PSNR is computed, and here all the waveforms are plotted, your original signal, noisy signal, and the denoise signal. So here now I will run this program, and I will show you that how you can get the output. So opening the Matlab, this is my editor, and this program is already written, right? So I'm just running it, and it asks me to select the audio. So I'm selecting the flute. So let me select the flute audio. So okay, it is done. Denoising is done, and you can see the corresponding waveforms, right? Which I have just shown, and now I will make you listen these audios. So on the command prompt, you have to write the command, that is the sound command with the sampling rate. So I'm writing sound XNFS. That means this is a noisy audio. So just listen it, and listen that how much background hissing noise because of the white Gaussian noise is there. So I'm just playing it, and listen. Okay, so in this 10-second audio, you have idea that how much background hissing is there. Now just listen the denoised output, okay, and see what's the difference. Okay, listen. Okay, so now you can see that the hissing is gone in this case. Now let me take one more audio. I'm taking Pakhawash now, and this is my output. So noise, original, noisy, and the denoise. And let me make you listen these audios. So first listen the noisy one, this one. Okay, so lots of background hissing noise. And now listen this denoised one. Okay, so this is much better. Even if you fine tune more and applying some more combinations, even it can be made better. Okay, so this is about how you can run this program. Now come to the comparative study. So this is the table which shows the PSNR of uh, between the actual, I mean, noise-free audio and the denoise audio. So here I'm studying the label of decomposition effect. So here I have taken the audio of Pakhavach, Wavelet Sim4, and the soft thresholding is used wherever it is applicable. And level of decomposition I have used from 1 to 8. So first see the universal threshold. So this is the PSNR at the label 1, for the level 2, 3, like that. So here I have highlighted the highest PSNR, which is opt-in. So for universal threshold, I have opt-in the highest PSNR at level 2. And when I increase the label, its PSNR is decreasing. Next is the sure method. Here at the label 5, I'm getting the highest. And initially it is also low, but when you increase the level of decomposition, it is going up to the 39, and it is almost around the 39. For min-max, I'm getting highest at level 3. For base, I'm getting at the level 6. For block.js, level 4, and FDR level 3. So although for min-max and FDR, I'm getting highest at level 3, but when we listen the audio, denoise audio, we found that the audio quality, I mean listening quality, is better only after level 4. So L equal to 4 or greater than 4 is acceptable for any threshold method. So 4 is I have found to be more optimal. So you can see that all values are around level 4. And in the next table, we are just comparing the wavelets also. So we have taken the DB3 COIF 5 Bior 6.8 and Simlet 4. So here for the Pakhavach audio, which is decomposed at level 4, we are finding the PSNR values for all these noise estimation methods. So see the universal threshold, it gets the maximum PSNR for Bior 6.8, Biorthogonal 6.8. And sure gets highest PSNR for Wavelet, Minimax for Biorthogonal 6.8, base for COIF 5, block.js for COIF 5, and FDR also for COIF 5. So it means, and the highest is we are getting with the sure and COIF 5. So obviously the Wavelet 5 is performing better as compared to all other wavelets for the Pakhavach audio, and the sure method is giving me the highest PSNR. So sure and COIF 5 combination is working well for this Pakhavach. And in the next, for flute, again universal threshold is also giving highest for COIF 5. Sure is also for COIF 5, and all other are for COIF 5 except this FDR, which is for Biorthogonal 6.8. So again we will see that Wavelet 5 is performing better, and again the sure is giving me the highest PSNR as compared to all other PSNR. So the sure and the COIF 5 combination is still working well for flute. And for Shehnai, again, the sure and is giving me the highest PSNR, but now it is giving me with the Biorthogonal 6.8. COIF is also not far behind. It is almost equal to the Biorthogonal 6.8 PSNR value. And base for COIF, block.js for COIF, but here for Shehnai, the things are shifting towards the Biorthogonal 6.8. So for Shehnai, you can say you can go for Biorthogonal 6.8, and but sure method again is giving me the highest PSNR value. And for tabla, again the COIF is the winner. You can see all the highest PSNRs I am getting for COIF, but block.js is giving for Biorthogonal 6.8. But again the sure method is giving me the highest PSNR for COIF 5. So sure and COIF 5 combination is again working well for tabla audio. And for Tanpura, again all thresholding methods are giving highest for the COIF. And again sure is at the highest PSNR again. So COIF 5 and sure combination is working best among all these combinations. So that is clear. So now come to the outcomes. So we have found that level of decomposition must be either equal to 4 or greater than 4. That gives a better denoising audio. And out of the wavelets which we have considered like DB3 COIF 5 and Bior 6.8 Sim 4, COIF 5 is found more appropriate to give the maximum PSNR value, and out of the threshold methods, we found the sure to be the best. So we have found that COIF 5 and the sure combination is best for various these Indian musical instruments. So this is all about this lecture. I hope you have enjoyed it, you have liked it, and you have learned something new. So I have covered the how the denoising is implemented in the Matlab, and we have done the comparative study of various noise estimation methods, and we have also compared the performance of various wavelets, and we have found that Wavelet 5 and the sure method combination works best for these audios of some Indian musical instruments. For some other audio, this combination may not work. You have to find comparatively the other better combination. So thank you very much for watching this video and spending your time with me. Once again, I thank you, all of you.